Hello learners, welcome back to my channel Shraddha's Physics. In this part we will see the quantum mechanics of the simple harmonic oscillator. That is, in this part we will see the energy levels and the energy eigenfunctions of the simple harmonic oscillator, and that after we will see the 0 point energy or the ground state energy of the simple harmonic oscillator. So by using the Schrodinger equation we can solve this simple harmonic oscillator problem. So first of all, in the simple way we can see the linear or the simple harmonic oscillator. So first of all, let us consider a particle having the mass m and that executes the simple harmonic motion along the x direction. Okay, so here you can see this body, it has the mass m and it is a rigid support, and this one is your spring, and this spring is attached with this mass m. Okay, and suppose this is the equilibrium position, that is x equal to 0, and after some time it is being stressed, that is having the spring of force constant k, so that the body will be get displaced from the position, from the equilibrium position to this displacement will be x. Okay, so here we can write the angular frequency omega will be equal to this spring constant k divided by m whole root over. So from this expression, that is if I will calculate the restraining force, so from that expression we can basically calculate the potential, so that we will use in the Schrodinger equation. So our basic aim is to calculate the potential energy here first. So the restraining force is directly proportional to the minus x. So here we can write F will be equal to minus kx, that is k is the spring constant, and here we can write in place of F that is force equal to mass into acceleration, or this is your m into d square x by dt square, that is force equal to mass into acceleration, and that is equal to minus k into x. Now if I will divide this m on the right hand side, so we will get d square x by dt square will be equal to, this is your minus k by m into x, and you know omega equal to k by m root over. So here we can put, if I will square both sides, that is omega square will be simply k by m. So in place of k by m, simply we can substitute omega square. So here this d square x by dt square will be equal to minus omega square x. And here the force equal to also we know mass into acceleration. So in place of the acceleration, we can substitute, this is your minus omega square x. So that will be equal to F equal to minus m omega square into x. Okay. And also we can write the force equal to the negative gradient of the potential, that is F equal to minus dV by dx, or if I will write minus dV, that is equal to, or dV integration will be equal to minus f dx. So from this expression we can write, since F equal to minus dV by dx, so from this expression we can also write that implies F into dx will be equal to minus dV, or we can take this negative sign to this side, or we can write dV will be equal to minus f dx, and also we can integrate both sides. Now if I will integrate both sides, then this minus, the value of f is minus m omega square x, so minus into minus becomes plus, m omega square x dx integration will be equal to m omega square is constant, x dx integration will be x square by 2, and you know the integration of dV is your v. And also we can write this is equal to, since omega equal to the root over of k by m, or we can write omega square equal to k by m. So here m into omega square, we can write m into omega square will be equal to k. So here we can write in place of m omega square, this will be k, and this is 1 by 2 into k x square. So this is our expression for the potential energy, that is V equal to half k square. That is when a particle having mass m, it is stressed from the fixed position, some position. So for that, and it is stressed from the rigid support. So for that the potential energy will be equal to 1 by 2 kx square. So now here we will first consider a particle undergoing the simple harmonic motion in one dimension, and that is called the one dimensional harmonic oscillator. The Schrodinger time independent equation in the one dimensional system, we can write the d square psi by ds square plus 2m by h cut square whole into e minus v of x into psi equal to 0. This is our Schrodinger time independent equation in one dimensional motion. Simply, in the application part of the Schrodinger equation, we are simply substituting the value of the potential energy, and here for the simple harmonic motion, this V of x equal to 1 by 2 m omega square x square, okay, or simply we can write that is equal to 1 by 2 kx square, okay. And here if I will substitute the value here, this will be 2 me by h square square minus, in place of v we have substituted this value, that will be m omega square x square divided by h square square, because this 2m by h square square is being multiplied with the first term as well as the second term. And now here if I will write this lambda equal to 2me by h square square and alpha equal to m omega by h square, then this equation can be written as dou square psi by dou s square plus lambda minus, this is your alpha square x square psi, that is equal to 0, okay. So why we were substituting this value? Because we have to calculate we have to solve this equation number 2, we have to solve this equation. So here the solution, it is equal to the product of the asymptotic solution and the power series solution of the lambda. Now for the asymptotic solution of the lambda, that is when the x is very large, or we can say when this lambda is very less than that of your alpha square x square. You can see here the lambda value equal to 2me by h square square. So here if we will consider lambda to be very less than that of your alpha square x square, so here we can write dou square psi by dou s square, and if you will neglect this lambda term here, this will be minus alpha square x square psi, that is equal to 0, because here we are considering the wavelength, it is very less as compared to your alpha square into x square. That's why we have just neglected that term, and we can write this delta square psi by del s square will be equal to alpha square x square into psi. And if you solve that equation, you will get the solution to that equation will be psi equal to exponential plus or minus alpha by 2 x square, okay. So here you can see there are two solutions, that is exponential plus alpha by 2 s square, and another one is your exponential minus exponential minus alpha by 2 s square. So there are two solutions, but here the positive, that is exponential alpha by 2 s square, it is unacceptable, because when x tends to infinite, you can see here when x tends to infinite, this exponential alpha by 2 into s square, this term also goes to infinite, that is psi tends to infinite, that is which is impossible. That is, we know the psi should be finite in nature. That's why we have to consider the only solution is psi equal to exponential minus alpha by 2 s square, and this is called the asymptotic solution. And now when x tends to infinite, you can see when x tends to infinite, that is 1 by exponential alpha by 2 s square. When x tends to infinite, that is 1 by infinite, and that is equal to 0. We can simply say this psi tends to 0 when x tends to infinite. So this must be satisfied for a well-behaved function. Now we will see about the power series solution. That is that equation is the linear combination of the power series solution and the asymptotic solution. So now you will see the power series solution. Now if I will write the solution, that is psi equal to this exponential minus alpha by 2 s square into any function, that is your f of x. Here this is your f of x into this much. Now we can, if I will take the partial derivative with respect to x, then dou psi by dou s will be equal to, these are the two terms are present here. So the first of all we will write f prime of x into exponential minus alpha by 2 s square minus, for this part this will be minus alpha by 2 into 2x. So the 2 to get cancelled, that will be minus alpha x f of x into exponential minus alpha by 2 x square. And similarly you can take the second order derivative of that psi. So after solving this, you can see the equation number 6 is your dou square psi by dou s square. Now if I will put all this in equation 2, that is in this expression, that is dou square psi by dou s square plus lambda minus alpha square square psi equal to 0. So here the value of dou square psi by dou s square equal to this much plus lambda minus alpha square square into this is your psi, that is equal to 0. And now if you will solve this one, then you can see here this is f double prime of x minus 2 alpha x f prime of x, and here it is minus alpha f of x plus alpha square x square f of x, and here we can take common exponential minus alpha by 2 x square. So here this alpha square x square f of x and this is your minus alpha square f of x, this term get cancelled. So this is finally we can write f double prime of x minus 2 alpha x f prime of x plus lambda minus alpha f of x, that is equal to 0. Now if I will change this y equal to root over of alpha x, that is if I will substitute y to be root alpha into x, then this d by dx also can be written as, if I will multiply this dy here and also dy here, that is in the denominator and the numerator, then this will be equal to d by dy into dy by dx, and since y equal to root alpha into x, so we can calculate dy by dx will be equal to root over of alpha, because dx by dx will be equal to 1. So in place of dy by dx we will write root alpha into this term, that is d by dy will be present here. Again if we will take d square by ds square, then this will be equal to d by dx of d by dx, and here the value of d by dx is root alpha into d by dy, and also this d by dx is your root alpha into d by dy. Simply this is root alpha into root alpha, that is alpha into d square by dy square. Okay. So now here you can see, if I will substitute this f of x to be the Harmonic polynomial, that is your h of y, so here you can see that is the Harmonic polynomial is the solution up to that equation. So now we can write for that equation 7, this expression you can see here. This expression is quite similar to the Harmonic differential equation, that is f double prime of x minus 2 alpha x f prime of x plus lambda minus alpha into f of x equal to 0. So in this part, in this equation, if we will substitute the value, we will get alpha into d square by ds square. This is your h of y, since it is the solution of the equation, then we can write this is your minus 2 alpha y root over alpha into root alpha d by dy into h of y plus lambda minus alpha into h of y equal to 0. Okay. Simply we have substituted the values here. That is, if I will write this expression, that is d square f by ds square minus 2 alpha x df by dx plus lambda minus alpha into f of x equal to 0. In that part, we have simply substituted the value, that is, you know, d square by ds square is nothing but your alpha into d square y by ds square, and so here this alpha into d square by y, d square by dy square, and your the solution is your h of y, that is in place of f of x we have substituted, that is your h of y. You can see here, in place of f of x we have substituted h of y. And now you can see here, if I will divide alpha, so here this will be d square y by dy square into h of y minus 2y dy by this root alpha get cancelled. So this alpha divided by alpha will be 1, 2y into d by dy of h of y plus lambda by alpha minus 1 into h of y equal to 0. So this is the Harmonic differential equation. So when we will get the Harmonic differential equation, so now we can apply the Frobenius power series solution method. That is, we can write this is your h of y will be equal to a n yn sum over n equal to 0 to infinite, and h prime of y will be equal to n a n y power n minus 1 taking the derivative, and similarly h double prime of y will be sum over n into n minus 1 a n, and this y power now becomes n minus 2. Now here if I will apply this 9a, 9b, 9c in the equation 8, if I will substitute all these values here, then we will get the final expression like this. Okay. So this equation is valid when the coefficient of yn is equal to 0. So finally solving this equation, we will get this a into a n plus 2 will be equal to minus lambda by alpha minus 1 minus 2n whole divided by n plus 1 whole into n plus 2 into a n. So this is the recursion formula, that is a n plus 2 equal to this much. Now our main aim is to calculate the energy eigenvalues of the harmonic oscillator. So here if I will write, you can see from this recurrence formula, if I will write this a n term to be 0, then all the even terms, that is this 0 plus 2 will be 2, then 2 plus 1 plus 2 is 3, and so on. Or we can simply say that if a is 0 equal to 0, all the even terms they will vanishes. So if a1 equal to 0, or if I will say if a1 equal to 0, that is all the odd term, it will vanishes. Therefore we can say we have an infinite number of solution. So to have a physically acceptable solution, we will choose the value of lambda for which n is an integer such that all the terms beyond two values of n, it will become equal to 0. That is, an plus 2 equal to 0 is the least acceptable term of the a is thus n. Or we can say simply, in a simple word we can say this an plus 2 will be equal to 0. It is the least acceptable term of a, that is we can write an plus 2 equal to 0. Since an plus 2 equal to 0, simply we can write this lambda by alpha minus 1 minus 2n equal to 0, because since this term equal to 0, 0 into this term, this total goes to 0, and divided by n also goes to 0. That's why we can simply write that is lambda by alpha minus 1 minus 2n equal to 0, or you can write lambda by alpha equal to 2n plus 1. And here you can see we have considered this lambda to be equal to 2me by h cot square. Now if I put the value lambda equal to 2me by h cot square and alpha equal to m omega by h cot, then this lambda by alpha now becomes 2e divided by h cot omega, because this get cancelled. So this will be 2e by h cot omega, and here in from equation 11 we can write this 2e by h cot omega will be equal to 2n plus 1, or simply e will be equal to 2n plus 1 by 2 into h cot omega, or simply if I will divide this 2 here, this will be e equal to n plus half into h cot omega. And here if you will put the value 0, 1, 2 and so on, that is when n equal to 0, this will be 1 by 2 h cot omega. When n equal to 1, this will be 1 plus half, that will be 3 by 2 h cot omega, and so on. When n equal to 0, here when n equal to 0, the value of e will be equal to 0 plus half means 1 by 2 h cot omega, and that is the ground state energy, and also this is called the 0 point energy. And when this integer, that is n, varies from 0, 1, 2 and so on, that is when you put the value n to be 1, then this will be 3 by 2 h cot omega, that is these are the energy eigenvalues of the harmonic oscillator, and there you can see they are equispaced. It means that when n equal to 0, this energy value is 1 by 2 h cot omega, and when n equal to 1, this will be 1 plus half, it means 3 by 2 h cot omega. So here this is your 3 by 2 h cot omega, and again plus 1, that will be 5 by 2 h cot omega. So here you can see the energy difference between these two will be equal to h cot omega. So here we can say these are your equispaced. Okay, and the lowest energy state of the oscillator will be equal to 1 by 2 h cot omega, and that is called the 0 point energy. Okay, now we will see the wavelength of the harmonic oscillator, and we have considered this lambda to be 2me by h cot square, and here we have substituted the value of e, that is n plus half into h cot omega. So if I will write the value of lambda finally, this is equal to lambda equal to 2m n plus half into omega divided by h cot 1, h cot is get cancelled with this h cot square. So the final expression will be lambda equal to this much, and that is the wavelength of the harmonic oscillator. Now we will calculate the eigen function of the harmonic oscillator. So here from this expression, that is from this differential equation, you can see this lambda by alpha minus 1 equal to 2n, we have substituted this value here simply, and here the Harmonic polynomial, this equation is in the form of the Harmonic differential equation. So the Harmonic polynomial, that is the solution to this differential equation, will be equal to minus 1 power n e power y square nth derivative of the exponential minus y square. So here the eigen function of the harmonic oscillator, we can write any normalization constant n into hn of y into exponential minus y square by 2. This is the solution of the equation. And here if I will calculate the normalization constant value, simply we have to take this psi n y mod square into dx, that is equal to 1. If I will put the value here, that is psi n mod square means psi n into psi n star. Since here no iota term is present, so here we can consider this is your nhn exponential minus s square by 2 into nhn of x exponential minus s square by 2 into ds, that is equal to 1. Or simply this is n square hn square of x into exponential minus x square into ds, that is equal to 1, because exponential minus s square by 2 minus s square by 2, so that will be equal to minus 2s square by 2, or that is simply 2 get cancelled, that will be exponential minus x square. And here we have considered y equal to root over alpha x, or we can write x will be equal to y by root alpha, or dy will be root alpha dx, or dx will be equal to dy by root alpha. If I will substitute these values here, now finally we can write this n square by root alpha taken common, integration from minus infinite to plus infinite, hn square y by root alpha exponential minus y square by alpha into dy, that is equal to 1. Okay. Now from the orthogonality condition of the Harmonic polynomial, we can write hn square of y exponential minus y square dy equal to 2 power n factorial into root over pi. These are your some mathematical calculation. So here hn square of y into exponential y square dy equal to 2 power n into n factorial into root over pi. So here if I will substitute these values here, this will be n square by root alpha into 2 power n into n factorial root over pi, that is equal to 1. Okay. So here this n will be equal to, from this equation we can take every term to the right hand side, so we will get n equal to root alpha by 2 power n into n factorial root over pi whole power 1 by 2. Okay. So here finally the wave function, that is equal to psi n equal to root alpha, that is n into the wave function psi n equal to n into exponential minus alpha x square by 2 into the Harmonic polynomial hn of y, or hn of root alpha into x. So in place of n, that is the normalization constant, we have substituted this value, and again we can write more precisely, that is equal to 2m nu by h cot root over into 1 by root 2 power n into n factorial hn of y into exponential minus y square by 2. Okay, here we have substituted the value of alpha also. So for n equal to 0, 1, 2, 3 and so on, we can write the value of root alpha by pi equal to m omega by h cot pi root over, and that is equal to, if in place of omega if I will substitute the value 2 pi nu, so we will get this is a 2m nu pi divided by h cot pi root over, and finally cancelling this pi we will write 2m nu divided by h cot root over. So this is the energy eigen function. This psi n represents the energy eigen function of the simple harmonic oscillator. Now you will see the 0 point energy is conformly with the uncertainty principle. So for the smallest value of n equal to 0, the energy of the oscillator, it is minimum, that is E0 equal to 1 by 2 h naught. This E naught, it represents the ground state energy or the 0 point energy. Basically we can say that in case of the quantum harmonic oscillator, that is the quantum simple harmonic oscillator, in that case the ground state energy is not 0, that is as in case of the classical harmonic oscillator, but here it possesses some energy, that's why it is called the 0 point energy or the ground state energy, and its value is equal to 1 by 2 h nu. So this is all about the simple harmonic oscillator, that is the quantum simple harmonic oscillator. So finally we conclude that the differential equation you will get, that is your Harmonic differential equation, and the solution you will get is the asymptotic solution and the power series solution. So after solving that, you will get the energy eigenvalue and the eigen function. Okay, so this is all for today. Thank you all.